Here, we are asked to calculate the lattice energy of Na2O, which is our sodium oxide. And we are given a list of reactions as well as the enthalpy values. Now, unfortunately, they didn't give us the actual reactions. They only gave us what the actual reaction names are. So what we're dealing with here is going to be the Born-Haber process, or the Born-Haber cycle. So the Born-Haber cycle, we basically just add up all of these reactions in order to get to our lattice energy based on all of this information. So the most fundamental thing about the Born-Haber process is first understanding, number one, what is the reactions in play, as well as what is the final reaction that we're looking for. So you should be able to look at every single one of these 7 reaction types and write out what the reactions are. But not only that, you have to remember that the sum of all the enthalpies of your reaction steps times whatever their coefficients are going to be will equal the enthalpy of your final reaction. Whenever you add those reactions up, that final reaction is just the sum of all of those enthalpy steps. Now, the M value, that coefficient, is based on what you do to manipulate each step. So if you were to flip a reaction, that M value is going to become a -1. If you multiply it by some number called x, your M value is simply going to be the x value, so we're going to multiply it. If you do both flip the reaction and multiply by x, your M value will be a -x value. And this is just that coefficient that you multiply by some h value. So if you have these 6 reactions, then you're going to have 6 different enthalpy values, each one possibly being manipulated. So it's going to be a very good idea to not only know your reactions, but you need to be very organized here. It is going to be very important for you to write all your steps out in an efficient way, but to do so without dropping anything and trying to keep a track of everything that you've done. But again, the biggest fundamental thing about this is what are your reactions that you're working with? So keeping this in mind, we need to break down all of these reactions just so we know what we're working with. What I went ahead and did was I went ahead and rewrote all of these out. Again, our goal is to get our lattice energy. So the lattice energy reaction is going to be the gas ions of the solid that we're working with yielding 1 mole of our solid. All right, so we have 1 mole of our sodium oxide solid. We take a look at all of the gas-based ions in order to do so. So our goal of the reaction is simply there. And as I mentioned, the enthalpy of our final reaction is the sum of all the enthalpies that we're working with times some coefficient that we manipulate. Now, one thing that I want to point out to you is this last step, this enthalpy of 5 times 6, or 5.6. It's not multiplied, it's just a way I'm notating it. What I've done is, as you can see here, I've listed all the reactions in 1 through 6, and I wrote out what the reactions are. So the enthalpy of formation for Na2O is not the same thing as lattice energy. Because yes, you will have a solid and a sodium oxide, but the enthalpy of formation are the elements in their standard states, so long as you make 1 mole of product. So sodium solid is the standard state for sodium, and O2 gas is the standard state for oxygen. And we put values in front. And this is the only time, the enthalpy of formation is the only time you can have a half value in front of a molar coefficient. The second one, sublimating sodium, means that you're doing a phase change. So you're going from a solid to a gas, because that's what sublimation is. The bond energy, you're going to start with what the bond is, and then you're going to break it up. So your product should be elements. So my bond energy for oxygen is going to be O2 gas yields 2 oxygen gases. Your ionization energy for sodium starts as a sodium gas, so the element in question, and since it's ionization energy, it's the amount of energy you need to remove an electron. So an electron will be a product, and then you're left with an ion, the single positive charge ion. But what I've done for the last 2, 5 and 6, is I can combine them, because my 5th reaction is the first electron affinity for oxygen. So it's going to be my oxygen gas plus an electron will yield O negative gas. While my second electron affinity, and this is very particular here, the second electron affinity starts with the first ion. So you're not starting with O gas, you're starting with O negative because it's the second affinity. It's the second value in which you're adding just one electron, and you're going to get an O2 negative. So the first and second electron affinities, or the first and second ionization energies, the reactants are not the same thing. You're always adding one electron or removing one electron. So for the first electron affinity, you're going from O to O negative. The second electron affinity, you're going from O negative to O2 negative. But what I did was I can actually add these reactions up, because notice if I add the 5 and 6 together, my O negative gas can cancel because I see it both on the left and the right hand side. So that is what I did. I combined the 5th and 6th, leaving me with O gas plus 2 electrons yields O2 negative gas. And since I added those up, I know that my enthalpy for my combined reaction is just the enthalpy for 5 and the enthalpy for 6. So from here on out, I'm no longer going to refer to these as formation or sublimation or ionization energies. I'm going to refer to them as numbers because I can remember, oh, reaction 1, reaction 2. I've already labeled it. Here's the problem. How do we start this? Well, the nice thing about doing reaction equations and these step reactions and adding them up is you can start wherever you want. The starting point is essentially going to be whatever is the most obvious item in these side reactions to get you what you want. And what I want is 2 sodium gases on the left-hand side, 1 oxygen, 2 negative gas on the left-hand side, and I want 1 Na2O solids on the right-hand side. And I already know where I can get that. I can get that from the first reaction. So what I'd like to do is I'm going to start with reaction 1. And I'm just going to rewrite reaction 1, which is 2 Na solid plus 1/2 O gas yields Na2O solid. And as of right now, I'm already happy. I have what I want. I have one part done. I now need to start eliminating things. Now, this is up to you and which one do you want to start with. Do I want to eliminate the sodium solid first, or do I want to eliminate the oxygen first? It's really up to you. For me, I kind of want to go ahead and get rid of the oxygen first. So my next step, if I look at my reactions, and remember, once you use one reaction, you're done. So my first reaction is done. I now want to use my third reaction, because if you notice, I have an O2 gas. And in order for me to use my electron affinities, I need to get rid of my O2 and make it just simply O gas. So I'm going to use my third reaction, and I need 1/2 O2 gas on the right-hand side because I need to eliminate this. So I need to do something to get 1/2 O2 gas on the right-hand side to my third reaction. So, third reaction, O2 gas is on the left, so I know I need to flip that reaction, and I will need to multiply it by 1/2. So I'm going to flip and then multiply by 1/2, which will mean that the 2 O gas on the right-hand side now becomes 1 O gas on the left-hand side. And when I add these reactions up, my 1/2 O2 gas goes away. Now that I have one gas, I can get my gas ion, because that's what I need. I need to get O2, I need to get an O2 negative charge on the left-hand side, which would mean, so 3 is done. The only thing left to do is now work with my 5th and 6th reaction. So I have O gas on the left, 2 electrons on the left, and one O2 negative on the right. So I want that O2 negative on the left-hand side. So I'm going to take my 5th and 6th reaction and just flip it. So 5, 6, I'm just going to flip. And I will write this down as O2 negative gas yields 2 electrons plus O gas. Now if I was to stop here and add all of these up, my O gas on the left and the O gas on the right are going to cancel. So you always want to check every time that you write your next step, check to see what cancels. And now I have O2 negative gas on the left-hand side, so I'm good there. I now need to figure out a way to eliminate my 2 sodium solids. And I only have two reactions to work with here. I have my second reaction and I have my fourth reaction. My goal is to get 2 sodium ions on the left-hand side. Those sodium ions are gas form. But if you look here in my reaction, I'm starting with sodium solid. So I really need to work with that second reaction, that sublimation reaction first, which was my second reaction. Sublimation was 2, yep. And since I want to get the sodium solid on the right-hand side so I can eliminate it, I'm going to flip the second reaction, but I also need 2, because notice I had 2 at the beginning. So I'm going to flip and multiply by 2, so we'll have 2 sodium gases on the right-hand side. So my 2 sodium solids now go away, leaving me with 2 sodium gases. And this is nice because the only reaction I have remaining is my fourth reaction. And if you look, my fourth reaction has electrons to work with and my sodium gas to sodium ion gas. I need this sodium ion gas on the left-hand side, and I need 2 of those. So I'm going to flip my fourth reaction and multiply that by 2, and I will get 2 sodium ion gases plus 2 electrons will yield my 2 sodium gases. And the nice thing about this is not only does the 2 sodium gases cancel, but the 2 electrons that I had previously from my electron affinity of oxygens, those can finally go away because they cancel with the 2 electrons that I got from that ionization energy. And if you look, I now have the 2 sodiums on the left that I want, so 2 sodium gases plus my O2 negative gas yields Na2O solid. This is the bulk of the work for the Born-Haber process. Once you get this, plugging everything into the equation or the enthalpy calculation is simple. We just got to figure out what we did. So I'm just going to rewrite everything out here in a second. So I just rewrote the enthalpy sum for my lattice energy as my first reaction, second reaction, so forth. But note, and I went ahead and plugged those values in. But notice I have these series of these empty parentheses. I will put what I did to those reaction steps in those parentheses. For instance, if I go back with all of the stuff that I did here, you'll notice that I have all of these notations to remind myself of my values that I'll use. My first reaction, I didn't do anything to it. So I'm going to multiply that enthalpy of my first reaction by a positive 1. My second reaction, if I look, my second reaction I flipped and I had multiplied it by 2. So my second reaction will be multiplied by a negative 2. My third reaction step was flipped and multiplied by a half. So I'll put a negative 1/2 in front of there. For my fourth reaction, if I go back, my fourth reaction, I flipped and multiplied by 2. And for my fifth and sixth reaction, I flipped. So I'm going to put a negative 2 in front of my fourth enthalpy value and a negative 1 in front of my enthalpy for 5, 6. This is where people get confused when they do this last step because there's so many negatives and positives to worry about. There's a reason why your calculator has a parentheses button. Use those parentheses buttons liberally because you do not want to confuse losing or dropping negative signs. All right, so be very cognizant of that. And here I went ahead and did an extra step where I found every single value separate. So negative 414 minus 218 minus 249 minus 992. And then I have the minus 703, and these are all in kilojoules per mole. And I get a value here for the enthalpy of my lattice energy equaling negative 2,576 kilojoules per mole. And if we recall back to what we know about lattice energies, they should be large values and they should be negative values. This works here. So your goal for the Born-Haber process is to make sure that you do all the steps, you write everything out, you try to be as organized as possible, and you need to remember that if you manipulate any of those reaction steps, what that means for those enthalpy values. So again, just taking the sum of all of those reaction steps will get you that final enthalpy, so long as you recall if you flipped something or you multiplied your coefficients. But the big key here, not only to remember how you add reaction steps, is that you understand what the type of reaction will look like. So if I told you lattice energy, you should be able to write out what lattice energy is, the actual reaction, and so forth. Without that, you won't be able to do this problem.